So, good morning, everybody. Am I audible?
Good morning,
Yes,
sir.
sir.
Good morning, sir.
Okay.
Yes, sir.
Yes.
Audible.
Okay. So, we start our lecture on heuristic search methods today. We have already done what are the state space methods. And there, in the state space method, we study that there is a concept of a state or configuration, a set of variables, and domains of every variables to what are defined as valid configurations, a set of state transformation rules or moves from which we get an implicit state space graph. Typically, this graph is very large and cannot be stored. It could be infinite in some directions. However, the state transformation rules are finite. That means that the number of rules are finite, and for every rule, the number of children generated are finite. There is an initial or start state and a set of goal states. And as we have defined that these state transformation rules can produce OR nodes and AND nodes. Currently, we will study only OR nodes. We can therefore, if it is only OR nodes, then the solution from start to goal is a path in the implicit graph. The search space is systematically explored by a search algorithm. And this systematic exploration of the search space, we have seen three kinds of algorithms. We have seen breadth first search, we have seen depth first search, and we have seen, what is the third algorithm we have seen?
Iterative deepening search.
Iterative deepening search. We have seen these three kinds of algorithms. Now, today we will start the concept of heuristics, which are domain specific information. For every problem, you have different kinds of heuristics. And today we shall see some kinds of heuristics and how these heuristics are mapped into a common function and how these functions are used to solve the search problem. We have already seen the traveling salesperson problem the other day. How many of you have used the sliding tile problem before? How many of you have played with the sliding tile problem? Anybody? That there is this 9 moving squares, and then there's a blank square, and in every move you can move one blank square. So what would be the state space representation of the sliding tile problem? It's obvious. It will be a 3 by 3 matrix, which can take values 0 to 8 or 1 to 9, depending on how we encode the blank tile. And then you can define your moves and things like that. The other problem where there is a bag and coins and some gold bars and etc., platinum rings, etc. shown. This problem is a very famous problem known as the knapsack problem. Can anybody tell me what is the knapsack problem?
There is this knapsack where it has some value assigned to it, that maximum of that value we are trying to get from all the values possible. So maximum profit we are trying to get from the assigned values. Like here some values are given. So we are trying to get the maximum profit, but the knapsack contains a maximum weight. So amongst the weight we have to take whichever gets our we can get the maximum profit out of this.
Thank you. Thank you.
Yes, thank you,
So
sir.
we have a set of objects. The set of objects is S1, S2 up to Sn. Each object Si has a weight Wi and a profit Pi. the total capacity of the knapsack in terms of weight is C. My objective is to find a subset T which is a subset of S such that, can anybody else tell me what are my conditions? Where T a subset of S where T is equal to T1, T2 up to Tm such that
Total weight of T is
summation Ti I equal to 1 to M is less than equal to
C.
C, and among all possible such T's, we maximize what?
Profit.
Summation of
Total profit.
Profit.
Ti for all T. So we want to maximize the profit. What is the difference between the traveling salesman sliding puddle on one side and the knapsack problem on the other side? What is the difference between? Yeah, so this is a maximization problem. And the other two are minimization problems. Good. So now, given such problems, which could be maximization or minimization, for which we have state definitions, what would be the state transformation rules for the knapsack problem?
You can either take an object or leave an object and always be inside the weight limit.
Right. So what would be the state definition?
All the objects you have collected up till now.
Yes. So all the objects which have been taken up till now, a state is said to be a valid state if the total capacity is less than or equal to C, and given a state A, I choose an item which is not already taken, because here I have to take an item only once. So I choose an item xj, and I also decide not to take xj. So here I add xj to it, and here I retain a. So I use what is called the inclusion exclusion principle. I can use what is called the inclusion exclusion principle to create the state space. Can somebody else tell me what is the goal node definition here? How is a goal node defined?
Or we have already
another atom within the weight limit.
What, once more? Yeah, one is you cannot add another term, another item. In another means any other item. Here another means any other item. So you cannot add any item from the remaining list, isn't it? Please note that by this inclusion exclusion principle, we are considering one item at a time, and we are adding or removing it from the list. So in the state definition, other than just the items chosen, anything else is to be given in the state definition?
Total weight up till now, like.
Yeah, that you can calculate the total weight, the total profit you can calculate from the items chosen. And anything else in the state?
How much of quantity the weight left?
That also you can store because you know the global value. But for two different states, uh, is there any other thing that you need to do to decide
Total
on the
profit
goal node?
up till now.
Once more?
Total profit up till now.
That too you can calculate, yes. From the items chosen, you can calculate the total profit, you can calculate the total weight. And when you're generating the state, you can check whether it is a valid state or not. That means by adding that object, whether the total profit is exceeded, total weight is exceeded or not. Anything else?
What you did not pick up so far?
So there are two sets taken and remaining. For example, if A contains taken as T and remaining as R, this Xj must be there in R, correct? So here this will contain A plus Xj and R minus Xj, and the right hand side will be A, and what will be R now here? What will be the remaining set?
R
What
minus.
will be remaining? Again R minus Xj, correct?
Yep.
Again R minus Xj. So a state will have taken, remaining, and obviously from taken you can find out the total sum of weights and the total sum of profit. Both of them you can find out. That is not an issue. So one goal state is that you cannot choose any item from the remaining set and add it without exceeding the weight. That is weight limit. Any other goal state?
Empty remaining set.
Yes, the second goal state is empty remaining set. Good. So now, having obtained the idea of state space definition and recollected our thoughts on the state space definition, we come to the fundamental concept of heuristic search. So what is heuristic search? Heuristic search, other than state transformation rules, state space definition, implicit graph, initial, etc., we have this concept of heuristics. And this concept of a heuristic, as I said, is domain-specific information or problem-specific information. That means it is information about a problem such that we are going to find out, depending on the problem, how far we are from the goal. So let us assume for the time being that we are having minimization problems. For the time being, we will discuss minimization problems. Now, you remember our state space search, the breadth first, depth first search? What were the two lists where we stored nodes? What were they called?
Open and
closed.
And closed.
Open list and closed list. What was the difference between open and closed?
The vertices we visited were in closed, and we need to visit were in open some state.
So can you tell me what were the 5 steps of the algorithm? Initialize.
Select.
Second.
Select.
Select. Third.
Goal test.
Goal test. Fourth, expand. And fifth was continue, right?
Yes.
These were my steps. Now, open closed list contains all elements which have been expanded in step 4, right? Is that okay?
Yes, sir.
Okay. An open list contains all elements who are children of those who have been expanded, of nodes which have been expanded, but they themselves have not yet been expanded. That is our conceptual idea. Now, every node in open, we have discussed the other day that we could maintain a level value at open. That means what is the level from the start. Now, when there are edge costs, when there are costs on the edges, then obviously this level value will be updated to what value? When there are costs on the edges, this level value will be updated to
reach there.
yes. So level value will now be updated to cost, which is the cost of, for any node n which is in open or closed, cost of the current best path from S to N. So we will maintain, this is S, this is N, we will maintain the cost of the current best path from S to N. In addition, we will maintain what are called heuristics. So we will maintain another value called Hn at every n. Hn is equal to the estimate of the cost of the best path from n to goal. That means if there are many goal nodes G1, G2, G3, obviously from n I do not have the actual path from n to goal. If I did, then there was nothing to search. I would know exactly how to go. So I have estimates of the cost of the best path from n to goal. So these estimates are called heuristic estimates. And if because it's a minimization problem, if I use a function fn, which is gn plus hn, then this function fn, which is gn plus hn, is the estimate of the cost of the best path from S to goal via n. It has two components. One is the current best cost up to n and the estimated cost from n to goal. So the heuristic search algorithm uses what is called an evaluation function Fn equal to Gn plus Hn for the kind of graphs that we have chosen, where there are edge costs on the edges. It's a minimization problem, and we compute Gn during the algorithm, and for every problem we are given a kind of an Hn to use, and we will study what these possible Hn values are. Any questions? Okay, good. So now what we will do is we will modify our breadth first search, depth first search, and iterative deepening search using the heuristic estimates and the heuristic evaluation functions. So let us see some possible heuristic functions. This is back to the sliding puzzle problem, where we are given a start configuration and a goal configuration, and we know that here is our start configuration and here is our goal configuration. So this is our goal, and there could be many other paths to the goal as well. Now we know that we can move only the blank tile in one move. So given any arbitrary state, an estimate of moving from this state to the goal, one heuristic could be the number of misplaced tiles. That means how many tiles are out of place. This heuristic, for example, in this case, who is out of place for H1 is the first block 2, is it in place or out of place?
Out of place.
Out of place.
8 is in place or out of place?
Out of place.
This one is in place or out of place?
In place.
In place.
So 0. This one is in place or out of place?
In place.
This one is in place or out of place?
In place.
This one is in place or out of place? In place.
In place.
7. This is in place or out of place? So we get a value of 4. H1 says that an estimate of the number of moves from this node n to goal is 4 by misplaced tiles. Is it an underestimate or an overestimate or an exact estimate?
Underestimate.
This is an underestimate. Why?
So because it doesn't tell us anything about how far they are from the actual system, how those tiles
Not
are
only
far.
how far, the sequence of moves, because we know that one misplaced tile will require at least one move to go to its final position. So it is obviously an underestimate. The second heuristic is a little better. It tries to find out how many steps one node is away from its goal position. So suppose I give you a configuration like this. What would be H2? How far would this be away from its goal?
2 steps.
So can you tell me how far would 8 be away from the goal?
8, 1.
2, sir.
2.
2.
2.
How far would 4 be away from the goal?
1.
1.
1.
How far would 1 be away from the goal?
3.
3. How far would 2 be away from the goal?
3.
How far would 7 be away from the goal?
1. 1.
How far would 5 be away from the goal?
2.
2.
And how far would 3 be away from the goal?
3.
3. So for this, H2 is a total of how much?
How is 6 2 steps away from the goal?
In one, you cannot move in diagonal positions. No? You can either move horizontally or vertically.
Sir, the position where 7 is there, so that will be the ultimate goal of 6, right?
For 6, I think it should be 3.
This is the goal state, no?
Yes, sir.
This is the goal state. So
for 6, it will be 3 times.
Yes.
So 6, it will be 3, right? Everybody is okay with it now?
Yes.
Yes, sir.
Thank you. So how much is H2? Total?
18, sir.
18 steps. How much would H1 be for the same problem?
Five, sir.
6 is away, 8 is out of its place.
Sir, 8, sir.
4 is
All.
Sir, 8 all.
8.
all of them are out of their place. So it would be 8. H2 would be 18, H1 would be 8. Is that clear to everybody?
Yes.
Now, is H2 an underestimate or overestimate or sometimes underestimate, sometimes overestimate or exact or what?
It's either equal or underestimated.
Sometimes, I guess, overestimate.
How can it sometimes underestimate, sometimes overestimate?
No, sir, it is always overestimate.
Overestimate.
Underestimate, sir.
Sir, it is either equal to the actual cost or it is underestimated.
So it is always either equal to the actual cost or underestimate. Underestimate means that if the actual cost H star n is the actual best cost from S to goal, then the definition of underestimate is like this.
Sir, this is for H1, right?
Both H1, H2, both are underestimates in this problem.
Okay.
Can anybody tell me why H2 is also an underestimate?
Because those are the number of moves it will at least require to go into the goal.
Because in one move, a tile can move closer to its destination by one place. In one move, a tile can move closer to its destination by one place. So this sum of the distances will tell you that at least so many moves are needed.
Sir,
so that is why, yes.
Sir, but in another way, I can think that if I go from one place to another place, then I will, let's say, swapping the tiles. So
That is a
maybe.
different state space definition. You're changing the problem. To change the heuristic, you're changing the problem, na?
Yes, sir.
If you change the problem, then that is something else. If you change the problem, suppose you change the problem by you saying that I can swap, then is there any difficulty in solving that problem if you can swap? Can anybody tell me if I allow swapping, then does that problem remain difficult at all?
Sir, it's a different problem altogether.
Not only it's a different problem altogether, but is there any difficulty in the problem also?
Swap with its goal state.
Yeah, just swap.
There is
No
no difficulty at all, because then we can just swap and over.
Yeah, you can just write a sequence of how many people are displaced. That many swaps would be enough for you to solve the problem quickly. Okay, so among H1 and H2, what is your gut feeling? Which one is better?
H2, sir.
Yes, H2 is better because
Sir, it's a better estimate of the actual cost, even though it is
yes, it is closer to the actual cost. Good. So let us come to the second problem. Yes.
Sir, H star n equals to actual base cost from S to G or N to G, or via N S to G.
Sorry. N to G.
Okay, sir.
It is N to G. I am sorry. HN is the actual best cost from N to G. Does that clear your doubt?
Yes, sir.
Thank you. So now let us come to the traveling salesperson problem. In the traveling salesperson problem, we have discussed the state space definition, etc., etc. So now, there are two heuristic estimate costs that are defined here. Can anybody explain what is the first one? What is the first one? Can anybody explain?
the cost of the path from our current node to our starting position from the nodes that we have not yet explored.
Correct. Very good. That means we are at our current position, which is the last node in the sequence till now. And other than the start node and this node, all the other nodes which are already selected are removed from the graph. So I remove all other nodes other than the start node and the tip node which have been already selected. So if I am in a position like this, I have a sequence S1, S2 up to Sk. This is my current state, and there is a cost. Then other than this S1 and Sk, I remove all the other intermediate nodes from the graph. And then I find in the remaining graph, what do I find in heuristic 1?
The shortest path.
The shortest path from
Current
Sk
node
to
S1.
Yeah, S1. Sk to S1. So is that clear to everybody? What I do, I remove all the other nodes except the start and the current node. And then I find the shortest path from the current node to the start through the remaining nodes. Is this An underestimate or something else?
Underestimate.
This is an underestimate. Okay. So this is an underestimate. What is the second one? The second one? Anybody else?
Cost for the remaining nodes. So going through from the present state to the closed state.
Or what I again do is I remove these nodes from the graph, those intermediate nodes which I have already seen, and in the remaining graph I find the cost of the minimum cost spanning tree. By finding the cost of the minimum cost spanning tree, then I will get an estimate. But the minimum cost spanning tree, while it covers all the nodes by a tree, it is not a sequence of paths. Therefore, the minimum cost spanning tree will also be an underestimating cost. How many of you do not know what is the minimum cost spanning tree?
Sir, I don't know.
Yeah. So all of you who don't know what is the minimum cost spanning tree, please read this up. It will take a little bit of time for me to explain what is minimum cost spanning tree. So please read up minimum cost spanning tree of a graph and also the algorithms to find it. This is a very basic and traditional algorithm. It will not take you more than an hour to understand, and it has got a large number of applications. And for those who know what is an MST, which heuristic is better?
MST.
MST. Correct. Now suppose let me ask a general question. Suppose I have two heuristics H and H dashed, such that both are underestimates, and it is a minimization problem. And it's a minimization problem. And sometimes, so which heuristic should I use? Both are underestimates, that much I know. Can anybody tell me which heuristic I should use?
Whichever provides a tighter bound.
Well, so how would you get whichever provides the tighter bound?
H dash is greater than or equal to H, then.
No, but sometimes H dash is greater, sometimes H is greater. Then what do I do?
So we may choose that which one is most probable.
Most probable. See, both are underestimates.
Oh, that is fine.
Both are underestimates.
But sometimes
H is better, bigger, sometimes H dash is bigger. Then which one will I use?
We choose the larger.
Yes, we choose the max of H and H dash. At every node, we have this additional computation of computing both heuristics. But after computing both, we can take the larger of the two. Because the larger of the two will be closer to the goal, since both are underestimates. Right?
Sir, I had a question that I didn't understand why both are underestimates.
In this tile problem, both heuristics are underestimates, no?
Yes, sir.
So I am assuming that there are two heuristics to a given problem where you are told that both are underestimates.
Okay.
Sir, is there any way to find an overestimate?
Yes, you can find an overestimate? An overestimate, what would be an overestimate in the sliding tile puzzle problem? Or
Square
what
of
would be
sum
an
of tile distances from the goal.
square of sum of tile distances from the goal? Correct? Square of sometimes, but this would not be always an overestimate. This can be sometimes an overestimate, sometimes an underestimate. In the traveling salesman problem, you greedily solve the problem by choosing the minimum next edge to the, and you go on choosing the minimum next edge, and if that provides you a solution, then whatever solution you get by a greedy algorithm would be an overestimate. So getting overestimates is also possible, and but you won't get too many guarantees using overestimates. So we'll come to all that.
Sir?
Yes.
So for the traveling salesperson problem, how can we show that heuristic one is an underestimate?
So the heuristic one, you have understood what is the heuristic one, right?
Yes, sir.
So the heuristic one finds the shortest cost path from the current node to the start node through the remaining nodes. Correct?
Yes, sir.
Our objective is to find a path from the current node to the start node through all the remaining nodes. Correct?
Yes, sir.
Now, therefore, the basic shortest path need not go through all the remaining nodes.
Yes, sir. It can also directly go through. If there
Yeah,
is a
so it can, it can go through directly. It can cut short a few nodes and go. Therefore, the solution that needs to go through every node, the best solution that needs to go through every node will obviously be more than the best solution that just needs to go back to the start node through any subset of nodes from which there is a path, isn't it?
Yes, sir. Yes, sir.
So now, having understood heuristics and having understood what our problem goals are, we now have not only edge costs, but we also have at every node marked in red in this figure, we also have a heuristic estimate at a node. So now our graph to search has got edge costs. So every edge cost, our assumptions are every edge cost CNM is greater than 0. This is our one assumption. The other assumption is for a minimization problem, and we will use a third assumption, which is called the monotonicity assumption. The monotonicity assumption is a natural thing to assume. Otherwise, you can incorporate it in the algorithm. Suppose a node has got a child. So suppose this is node P and this is node Q, and let the heuristic estimate of node P be 10. Let the cost of the edge from P to Q be 5. Now I ask you, if I say that the heuristic estimate of P is 20 and all heuristic estimates are underestimates, then can you find out some fallacy? Given this, can you say something about this?
So 15. So the rest of the cost is will be at least, it's saying that it will be greater than or equal to 5 plus 10, but the the node P says that it will be greater than or equal to 20. So 20 has become an overestimate here.
No. I have told you that all estimates are underestimates. I've told you.
Yes, sir. So when I'm at P, I'm saying that the cost, the rest of the cost will be greater than or equal to 20. But when I come to Q, I have already accounted for 5 and I have 10 left. So it's like it's saying that it will be greater than or equal to 15.
Correct. So what does it say? It says that, sorry. So it says that this value can be upgraded to 15 and it will still remain an underestimate. The value at 10 can be upgraded to 15 and it will still remain an underestimate. Correct? Because I know that all heuristic estimates are underestimates, whatever is given. From this, I identify that this value at Q, though being an underestimate, its value can be upgraded to 15 based on the value at P and the cost on the edges. And we also already, yes.
So the cost at 10 will be 15 or at 20 will be 15, because from 10 is the edge value, so from there
you can make very good. You can make this one at P also 15. You can make Q 15. But which one will you do?
So I'm thinking P should be 15, because from there we can say that the underestimate is 15, and from 10 is a better.
Now
we are already saying it 10.
Okay, so right. No, tell me. A little while ago, you all told me that if I have two estimates at a node and both are underestimates, I will take the maximum of the two because that maximum of the two is more accurate. Isn't that what you just told me?
Yes, sir. Yes.
Because I know that if all are underestimate, the one which is closer to the goal is better.
Yes, sir.
Correct. So now use that argument here. I can make P15 or I can make Q15. Which one will I make?
So then I will make Q15 because it will
Correct.
increase the
Because that will make it more accurate to the goal. So in this case, the monotonicity property is that HP must be less than equal to HQ plus CPQ. If this monotonicity property holds, it is fine. If it is violated, then upgrade HQ to what? HP minus CPQ. If the heuristics are underestimates, we will assume that it is monotonic. And if monotonicity is violated at any point in time, we will upgrade HQ to HP minus HQ minus that H cost. Clear?
Yes, sir.
So now we are also given another property that all heuristic estimates are greater than or equal to 0. Yes, Anindita?
So my question was like, why are I didn't understand why are we updating Q?
Did you understand why we updated Q to 15 here?
No, sir.
Okay. Now we know, again let me repeat. P is 20. That much you have understood.
Yes, sir.
Q is given as 10. HQ is given as 10. You have understood. HP was given as 20. You are given HQ as 10.
Yes, sir.
That also you have understood. You know the H cost is 5.
Yes, sir.
You also know that both HQP and HQ are underestimates.
Yes, sir.
So now from that, if HP is 20 and the H cost is 5, can you not argue and say that HQ will be at least 15?
Okay, sir. Okay, sir. Yes, sir.
So HQ will be at least 15. That is the argument.
Okay, sir.
So now what we have said here is that this is the monotonicity property, and if it is violated, we can upgrade. It comes from our earlier understanding that the heuristic estimate, if it is an underestimate, the closer we are to the goal, the better we are. So that is why. As somebody said, we could have made P15 also, but that would make the heuristic less accurate. And if the heuristic is more accurate, what am I expecting to happen? If I have
Lesser
two
time.
heuristic, yes, that means here time will be measured as
Number of expansions.
number of node expansions. Correct, correct. So if I use a more accurate heuristic, my search will be less. This is the classical search versus knowledge paradigm in AI. Throughout everywhere, if you have more information, you need to search less. So now we come back to our 5 steps. In our 5 steps, we have assumed these 5 steps. We now modify our 5 steps of our traditional best breadth first search algorithm, and we modify those 5 steps of our traditional breadth first search algorithm to get what is called the best first search. We again recall that we are using an evaluation function Fn, which is Gn plus Hn, where Gn is the cost of the current best path from start to this node. Hn is the estimated cost of the path from this node to goal. And we use Gn plus Hn to create what is called an evaluation function, which is the cost of the path from S to goal via N. That is the estimated best cost. So now we will continue to compute Gn values and Fn values and Hn values at different nodes. So the 5 steps of our algorithm operate as follows. In initialize, open set contains the start node. GS is obviously 0. Fs is 0 plus Hs. And closed list is empty. The only 2 additions we have made are this. Now in select, in breadth first search, we were selecting the first node, or in depth first search, we were selecting the first node. Now since we are to find the minimum cost solution, an equivalent of breadth first search here would be to select the node from open list which has got
Minimum cost.
yes, minimum estimated cost. So select that node from open list which has got minimum estimated cost. If open is empty, we terminate with failure. So we select a node with minimum Fn. Then, like in breadth first search, we terminate at the first goal. If n is goal, we terminate. Now, how do we obtain a path from S to N. After we terminate, how do we obtain a path? Can anybody suggest? How
So
do
we
we
can
obtain a
trace it
path?
from the node to the starting in the tree.
So in order to trace back, we need to maintain one more pointer. We need to maintain another data structure, which is called the parent of N or Pn. Pn is the current best parent of N. And the current best parent determines what? What does the current best parent of N determine?
The previous node.
Yeah, but what does it determine? It determines
the previous node with minimum Fn.
So it determines the Gn value of the node also, no?
Yes.
Yes.
That means the Pn is that parent through which you got your Gn value. Good. So when you start, Ps is made null because S is the only node which has got no parent. So if in step 3 we did not find goal, then we would go to step 4. That means we would use the state transformation rules to generate the successors. N1 to Nk. We would put again like before, we would put N enclosed. Now we may have 2-3 cases. One case is that the node Ni, we pick each children one by one. That node Ni is neither in open nor in closed. So which means that this node is a new node. That means from the state transformation rules, we have not seen this node of the implicit graph yet. We have seen it for the first time. Once we see it for the first time, we will compute its Gn value, we will compute its Hn value, we will compute its Fn value, we will put this node Ni in open list, and what else we will compute based on the discussion we just had?
A parent. Best parent.
Pni will be equal to N. Correct?
Yep.
Yes, sir.
Now, for if that node Ni is already in open or closed, it could either already be in open or it could already be in closed. If it is in open, if it is already in open, then what could be possible? Could you come to it with a smaller path? Smaller cost path?
Yes, sir.
You could come to it with a smaller cost path. That means the current value of GNI, that means GNI is already in open and its current NI is already in open and its current value GNI is greater than the value, the new value that you come with. So this condition gets satisfied. That the current value of GNI is greater than Gn plus CNNI. That means the path through which you come. So you already have Ni in open. It has a GNI value. But the new path that you are coming from N, this new path, which is determined by Gn plus CNNI, this new value is smaller. So you would update this value. So you would update GNI to GN plus CNNI. If HNI is already computed, so you don't want to compute it again, but you would have to recompute FNI because GNI has changed. What else would you have to recompute?
Parent pointer.
Correct. PNI will now become N. Whatever it was, it will change to N. Now the question that we may ask is that we just said if it is already in open, what about if it is already enclosed?
Then we have already visited it with a lesser cost path.
Yeah, so we will have to prove, and we will prove that we have already visited it with a lesser cost path, given our assumptions that the cost estimate is greater than 0, the heuristics are underestimates, and we either have a monotonic estimate or we will upgrade it to a monotonic estimate. So we assume that we already have a monotonicity in place. So we will prove that. So these are the 5 steps. Is it clear to everybody what these 5 steps are? Anybody has a doubt?
So can you repeat the last step?
The question is whether it is already enclosed or not.
Yes, sir.
Yeah, so we will prove that you don't need to check whether it is already enclosed or not. We'll prove that later on. Normally, we would have assumed that it could come, but because the edge costs are all positive and the heuristic estimate is both an underestimate and monotonic, then we will prove that you don't need to check it. So we'll come to that proof. We have not done it yet.
Sir?
Yes.
In the previous examples, by the term underestimate, did you mean that we are estimating a lower cost than actual cost?
Yes.
Okay.
We are estimating a lower cost than actual cost. So now let us go through the execution of algorithm A star. The execution of algorithm A star is as follows. At every node in open list, I maintain 3 things. I maintain with every node, I maintain 4 things. I will maintain a GN value, HN value, FN value, and PN value. I will maintain these 4 entities. The GN, HN, FN, PN. So initially A, and what is the parent of A? Null. So parent of A is null. So open consists of node A and closed is empty. So this is step 1. Now after seeing step 1, where open consists of node A and closed is empty, and opens are 0, which is G of A is 0, H of A is 6, F of A is 6, and parent of A is null. Now can anybody tell me which node will be removed from open? Aditya Jirath? Aditya Jirath?
Hello, sir. Yeah.
Yes. Which node will be removed from open? You're doing something else in class? Are you doing something else?
No,
Checking the
sir.
internet, email. Then from this step, can you not say which node will be removed from open?
Sir, I was
Have you
having some
followed?
more doubts regarding the nodes one.
So why didn't you ask? What is your doubt?
Sir, like I have to rewatch the lectures, like the previous lectures first, because
Not only previous lectures, I have taken a painstaking effort to video record all lectures and give it to you 5 days before the class. And if you forget about the previous lectures. If you had concentrated for the last 1 hour, which I believe you did not, and you all are all quite able grown-up people, you all are not children and kids with lollipops in your hands. And in this problem, how many nodes are there in the open list now in step 1? You're not following anything, let me tell you, Aditya. And I'm going to ask people in the class once in a while, and if they don't answer such simple things, then your teaching assessment marks will go to 0. You all have to be treated like children because your parents are paying through their nose for the education that you get. And all these excuses are no excuses at all to me. You're sitting in this class and sleeping. Abhishek Chaudhary? Abhishek Chaudhary, are you there in the class? Hey, Shorashish or Poonam, whosoever is there, can you please mark out these guys?
Sure, sir. I'll take a note.
Akash Tripathi? Akash Tripathi? Good. Very good. Asim Manna?
Yes, sir.
Yes. So which node will now be removed from open?
So node A.
Node A. And where will it be put?
In closed.
In closed. Good. And who are the children of node A?
B, C, and D.
Correct. Now, B, C, and D. Very good. You know, unless you are treated as school children, nothing will happen to you all. Pampered till the core. Jayant Chaudhary, are you there?
Yes, sir, I'm there.
Yeah. So Jayant, for B, C, and D, what will be the GN, HN, FN, and parent of B, C, and D?
Sir, for B, the parent would be A, and GN would be 10, HN would be 5, and FN would be 15. And then similarly for C, like A would be the parent.
Good.
And
Okay, very good, very good. I got it. Kinjal Bhattacharya, are you there? Kinjal Bhattacharya, are you there? Krishna Priya, are you there?
Yes, sir.
Yeah. So Krishna Priya, in step 2, which node will be removed now from open?
B will be B, C, and D, and that should sorry, A and D will be removed.
If we
Yeah,
are
so A is already removed. Now in the algorithm, see our algorithm consists of 5 steps.
okay.
Initialize, select, goal test,
Expand,
expand,
and then same
continue.
again.
Now we are at step 2 of this row 2. Which node will be removed from open?
D will be removed.
D will be removed because it is the minimum FN. And it will be put in closed. And what will be now put in open?
The children of D,
Yeah. What are they?
G and H.
No. Children of D is G and H.
Yeah, G and H.
Correct. And the G value of node G is 11. Its H value is 1. And therefore its F value is 12 and its parent is D. For node H, its G value is 9, H value is 3, and F value is 12, and its parent is D.
D.
Good, thank you.
Thank you.
Now, L. Kushireddy, are you there? L. Kushireddy, are you there? Okay. Mayank Sonu, are you there?
Yes, sir.
Okay. Now, after this, when we have removed and we have put the children of D, now which node will be removed?
Sir, H will be removed.
Why not G?
Sir, it has minimum G of n. H has.
Yeah, but our objective is to choose the one with minimum F, na?
We can choose any of
algorithm. Yeah, we can choose any one of them. Correct?
Yes, sir.
We can choose any one of them. Good. So you have chosen H.
Sir, actually, there was some issue with my microphone, sir. What was the last question you asked? I missed the question, sir.
The question is which node will be removed? He
Okay,
said
sir. Okay,
H.
okay, okay. Okay.
He said H. I said here there is a tie
Between this
G
F
and
and
H.
between G and H node.
G
Yes.
and H node. So we can remove any one of them.
Okay, sir.
So let us remove H. We will try again by removing G and see what we have. So if we remove node H, then what comes into open? What happens to open? Nancy? Nancy
Sir, C
Shailesh
gets
bhai?
appended.
Yes.
Yeah,
Yes.
who is saying this? Who is saying this?
Uh, we left
Yeah,
with
somebody said.
PCG.
So Nancy, yeah. Now when H is removed from open, so
yes,
what are the children of H?
no one.
From H to C there is an arrow, no?
Yes.
So
C is the children of H.
Right, but C is already in.
C is already in open.
C is already in open. And
yes.
So what do we need to do if a node is already in open? What is the check we need to do?
We have to go with the goal from that point.
No. We have to check something. If it is already in open, it already has the GNI value, no?
Yes.
So it is already in open. It is already in open. So it has a GNI value, and I have come to it from another site, from main. So I have to check. And you did not follow when we discussed this step. When we discussed 4D.
Yes.
In 4D, what did we say? When you come to a node already in open, you have to check whether you have come by a shorter
or long path. Yeah.
Shorter path. So what is the current value, GN value in C of C?
What is it?
What is the current GN value of node C? You know, how we are going? We are going how people go in class KG. So the current GN value of node C is 11.
Yes.
Okay. So how did we come to node C? We came to node C originally from A. Here the current value of node C is 11 or 12. I think you are sleeping in class. If you all don't concentrate, I can teach all this in 20 minutes. Because I have given all of you video lectures beforehand. I am going like people go in KG class, teaching A, how to write A, how to write B, how to write C, like that. And if you all don't even concentrate in class, then I will not concentrate also.
But
Paras
it will be
Malli?
changed to 11, right? It's a shortest path for it.
That is what I said. That I asked you what is the current value.
Okay,
so
I missed the
the
current. So
current value is 12.
yes,
And
current
you are
is
going
12
to come
and
to
then
it with 11. So
yes.
this gets updated from 12 to 11. The F value becomes 16 to 15. And what is the other change that happens?
We will
wait. Paras Malli, what is the other change that happens?
The
corresponding
updation in
values change, right?
Yeah, no, you wait. Paras, you answer.
yes, sir.
What
So
happens?
the GN value is updated along with that FN is also updated.
Nothing else? Look at
And
the
so
two.
parent is also updated.
Parent is also updated. Good. So this is how that 4D step is executed. Now, Pati, Sumant, Kastur, are you there?
Yes, sir.
So now in the next step, which node is removed? After removing G and updating the value of C, which node is removed?
Yes, sir.
Sorry, after removing H, we removed H and updated the value of C. Now, in open, we have three nodes, B, C, and G. Which is removed?
Yes, sir. Let me check once.
You're not following?
I am following, sir, but I didn't go to the next step. I'm at the current step.
It's all written there. It's all on the screen, no?
Yes, sir.
Anyway, let me ask somebody else. I'm losing on my patience. Piyush Gautam?
Yes, sir.
Which node is removed?
Sir, G.
G will be removed. And when G is removed, which node is put back in open? What are the children of G?
Sir, J. J and only J is the children.
Oh, only J is. Look at the graph carefully.
Okay, J and H are the children. And
All
H
of
is
you, I will request you again.
closed.
I will assure you that if you concentrate, I will spend time. If you all don't concentrate, I will go very fast. There is nothing. All this I have done in the video lecture. I can just go through them like this, and finish it off. So now, where is H already? H is already in?
Already is in closed.
Right.
So we
And
only have
in any case, you are going to come to it with a larger cost. So I put only what in back in open?
J, sir.
J. And then let me ask somebody else. Shomik Pine.
Yes,
Are you
sir.
there?
Yes, sir.
Now what is removed?
Sir, now in open, the lowest Fn value is of J. So we'll
Right.
remove J.
We'll remove J. And when you remove J, what is the condition satisfied?
Sir, we have to do a goal check. So
Right.
J is satisfying goal check. So we
So
will
you
terminate
terminate.
with this.
We'll terminate with this. And then along the parent pointer, we will find the path.
Trace back it, yes.
Good, good. So now looking at this problem, we had an option of choosing in the row 3, we had an option of choosing H or G. We chose H, but if we chose G, then would we also have to choose H in after that? Suppose here, all of us remember that here we had G and H, both of them having the same cost, and we chose H. Suppose at that point we had chosen G. Can anybody tell me, so if we had chosen G instead of H, then what would open become?
So then we would have updated J earlier and we would have reached earlier.
We would have reached earlier. Then we would have B 10, 5, 15A, and then we would have got J.
C.
Oh, sorry, C would be still there. C would be what value then? What would be C?
C 11 4 15 H.
How will you get 11? We have not
Okay.
seen
So
the
yeah, sorry,
Yes,
sorry.
old
Old
value
value.
of C.
C 12
12,
14 16 A.
4 and 16.
16A. We would still have H at 9, 3, 12D. And from G has got two children, no? One is J, one is H.
H and J, yes.
So would we update the value of H because of this new path from G to H?
No.
No. Because the new path from G to H,
Is longer.
the new is longer. So there is no point in updating H. And we would add J, isn't it? Because we have expanded G, we would add J. This would become open. From here, this would become open. Is everybody with me?
Yes, sir.
Yes,
Sir.
Yes, sir.
Now what would be removed from open?
So H again.
Sir,
H.
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 Now H would be removed. So now H would be removed. And when H is removed, what would open become?
B, C, and J.
C will be updated.
B, C, and J.
C will be
C
updated.
will be updated, na?
Yes, sir.
Parent.
C will be updated.
And list will be the same.
Yes.
And this would become identical to this. These two will become identical. And now J will be removed. Is it now clear to everybody that if we took this way or that way, we would have still found the goal at the first step?
Yes, sir.
Yes, sir.
So
Sir, in
A11.
case J
Yes,
had
sir.
a very sir,
Yes.
in case one of the nodes had a very low FN, is it possible that taking some other path leads to the answer faster?
Let's ask this question. Now tell me, because the edge costs are positive, the heuristic estimates are non-zero and monotonic. So we have assumed the following. We assume the heuristic estimates are lower bounds, monotonic, and also we assume that Hn is greater than 0. We assume Cnm is greater than 0. All these assumptions are there.
Sir, I had a small
Yeah.
doubt.
Yes.
Sir, in here the beside the nodes that what it is written 6, 3, 4 in red. So those are the HN values, right? So did we
Yes, those are the Hn values. Yes.
So did we pre-calculate those before the A star algorithm, before
No,
working this?
whenever you create a new node, whenever you generate a new node, here, in this case, 4C, if a node Ni is neither in open nor in closed, so it's a new node, that is the time when you compute the heuristic. The implicit state space is not given to you, so you compute the heuristic. Given
Sir,
the
how is
current
heuristic is computed? Because I cannot see HNI to be computed. Like,
Okay, so let us go back and ask the question which we asked in the beginning of the class. If I give you a state of this sliding puzzle problem n, which is something like this, can you not compute the heuristic?
Yes, sir. From heuristic to we can use matrix and the probability.
So you have a heuristic function, no? I told you. So given any node, you can compute the heuristic.
Yes,
okay,
sir. So this is independent from the other part of the algorithm because that is computed just from the function independent.
It is computed independent of what? It is dependent on the state, no?
Yes, sir. But like Gn is also depending on the other states. So Hn is
Hn is, by definition, Gn is the cost of the current best path from S to N. So it's called the current best path. Hn is an estimate of the cost from N to goal, which is given a state, you will know what is the value of Hn. Correct? Clear?
yes, sir.
sir, can you give an example in this graph case how the HN is determined for the first node, like A?
Here, then I have to go to a particular problem and explain the Hn. Na? The Hn cannot come from just a value. If I give you a letter E, how will you find Hn from a letter E? This is an example which we are using to solve the problem. If we come to the problem like this, then at every node you know how to find the Hn. Na? If you have, I am giving you a general algorithm. In that general algorithm, I am telling you that for every state space definition, for every new different problem, there is a heuristic function Hn given to you. And when we solve this, we are solving it for a general case of a graph like this. We are not solving it for a particular problem. We are writing a general algorithm. Our objective in AI and search is to develop what are called meta algorithms. Right? Algorithms which will work on every problem provided we are given the sufficient information. So in this problem, we are given a function HN. Have you understood?
Okay. Okay, sir.
Yes, sir.
Yes, sir.
So now, in this problem which we have, I am making some statements. Given that the cost CNM is greater than 0, given HN is greater than equal to 0, given HN is less than equal to the H star n and monotonic. What statement can I make what statement can I make about one cost of nodes expanded in step 2 cost of nodes not expanded, cost of nodes selected in step 2. What statement can I make about the costs of nodes that are selected in step 2? Anybody? What is the property of the nodes which are selected in step 2? So first node A was selected, then node B was selected, then node D was selected, then node G was selected, then node H was selected, then node J was selected. What is the property that you observed?
At least that much cost f of n must be paid to reach to the goal.
That is true, but any other more observing property? Yeah, we know that they are all minimum Fn. That is written in the algorithm. That is not a property. That is the way the algorithm works.
Oh, F must be monotonically increasing.
Right. The F values are monotonically. Very good. Increase. Very good observation. Anything else?
So, since the app values are monotonically increasing, so we can say that the first we reach the goal, that will be the minimum one.
Yes. That means when we reach the goal, is everybody convinced this one is all right? Monotonically increasing, everybody is satisfied?
No, sir, I didn't understand that.
Okay, you did not understand. So, what does monotonically increasing mean, or monotonically increasing mean, rather it is monotonically non-decreasing. What? Who stated this problem that it is monotonically non-decreasing? Can you explain what did you say when you said this?
Sir, basically, since we choose a minimum f every time, we know that once we took an f, all the f's we took before it must be either the same or the lesser, which is why it's monotonically non-decreasing.
So right. So what she says, what Neha says, is that I have selected one node from open, which was the minimum in open. Let that cost of that node be x1. After that, after next time I come back to step 2, I select another node from open. Let its cost be x2. What is the relationship between x1 and x2? Let the fx1, what is the relationship between fx1 and fx2?
Fx1 is less than fx2 always.
Less than or equal to.
Yeah.
So is it now clear to you that why it is monotonically non-decreasing? Person who asked?
Yes, sir.
So this is clear. Now let me state the second point. That when we reach the goal in step 2, we have the solution is minimum. We have reached the best cost. How will you prove it? What is the guarantee? Who said this? Who made this statement?
Sir, me. Because because you have stated that the f values are always monotonically increasing. So
Right.
so whenever if we reach the goal second time, then it will be always greater than or equal to the first value.
Correct. So whenever you reach another goal after this, then that cost will be greater than equal to the one which is obtained before. Therefore, the first goal node is minimum. From this, what is the third observation that anybody can make? See, can anybody make a third observation? To make that third observation, I'm giving you a hint. The hint is as follows. The hint is, did you check for the goal node whether it was the goal node or not when you removed it from open? In step 2, when you selected a node from open, did you check whether it was a goal node before selection or after selection?
After selection.
After selection.
After selection. So since you have checked it after selection, any node that you could have removed from open could have been goal node. Any node that you remove could have been goal node, because when you selected it from open, you did not know whether it was the goal node or not.
Yes, sir.
So now can you combine A and B to make a more powerful statement?
That will be the
So
optimal.
Correct?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
A and B implies C. which means that whenever we remove a node from open, Gn is the minimum cost path from S to N. Correct? Correct?
Yes.
Then, yeah. So if that is the case, now is it clear to you why we do not check whether a node already, whether a node exists in open and whether we come to that node with shortest cost path in closed? We check in open, but we don't check in closed because it cannot happen, provided these conditions are satisfied. Provided these conditions are satisfied, it cannot happen. So whenever we need a node, remove a node from open, then this node, the Gn value to that node is minimum. So armed with these, we are now left to prove the last thing we are left to prove is that if I have got two estimates H1 and H2 and both are underestimates, both are underestimates of the optimal cost path, and if H1n is less than equal to H2n, prove that A star using H2n will expand fewer nodes. Sorry, this is not less than equal to, this is less than fewer nodes than A star using H1. This proof I leave it to you to do. I will not do this proof. Yes, somebody had a question?
Yes, sir.
Yes.
So, sir, you meant like we came to the conclusion that like if x1 is a node, and if I go to the next node that is x2, then f of x1 should be less than or equals to f of
Next
x2.
node, I don't go to the next node. Again,
Okay.
understand what I'm saying. I'm saying I selected a node from open in step 2 in iteration 1 and iteration I.
Yes, sir.
In the next iteration, I selected a node x2 in iteration I plus 1. I selected another node x2. At that time, x1 was the minimum node in open.
Yes, sir.
Then in the next iteration, again, this node is the minimum node in open.
That is x2.
X2. And I'm saying that fx2 will be greater than equal to fx1.
Right, sir. So, sir, when I selected x1, then there are two possibilities for no, there is only one possibility for x2, that it must have come after expanding x1.
It must have come after expanding x1.
Because
if it was already there, then it would have been expanded before x1 if it is less. If fx2 was less than fx1 and it was already in open, then it would have been expanded before x1. It would have been selected before x1. So the other option is it is a child of x1.
Yes, sir. So now,
and if the edge costs are positive,
yes, sir.
if the edge costs are positive and the heuristics are monotonic, then fx2 will be greater than equal to fx1.
Right, sir. So, like, if I have understood correctly, then if I go through the path from start to goal, my f value should be monotonically increasing or non-decreasing?
Monotonically non-decreasing.
Monotonically non-decreasing. Now,
Yes.
sir, I have one doubt, is that, let's say, basically the function fn is sum of gn and hn.
Yes.
So if I write, let's say Fni is equals to Gni plus Hni, and then let's say in my solution path, I go to the next node and I write Fni plus 1 is equals to Gni plus 1 plus Hni plus 1. Now these two components, Gn and Hn, I know that Gn will be strictly increasing because here the cost is positive, but the heuristic as we go towards the goal will be decreasing.
Yeah, but the heuristic, even if it goes towards the goal, it will satisfy the monotonicity property that I just talked about. Yeah.
Yes. Okay. Yes.
So that solves your problem, na?
Yeah. Yeah, sir. Now I got it. Okay.
So armed with all this, we can now come back and re-examine our properties. The properties which we listed were the properties of A star that we had listed out include the following. Wait, I don't know what screen you are seeing. Are you seeing properties of algorithm A star on the screen now?
Yes, sir.
Yes, sir.
Right.
Yes, sir.
Yes, sir.
So, given they are monotonic, heuristics are non-negative, lower bounds and edge costs are positive, we prove first solution is optimal. We also said no node in closed is ever reopened. Why? Because you have already found the best cost path. You cannot come to it again. Whenever a node is removed from open, its minimum cost from start has been found. And if that is the case, then if C star is the optimal cost from S, it is F star S, if C star is the same as F star S, then what can we say about every node having Fn less than C star? What can we say? Then every node having Fn less than C star will surely be
Expanded.
selected in step will surely be selected in step 2, correct? And every node, sorry, every node having Fn greater than C star will
Not be selected.
never be selected because the algorithm will terminate before that. Because the algorithm will terminate before that. So with these properties of algorithm A star, today at 5 o'clock, before we move to depth first branch and bound, today at 5 o'clock, I will give you a set of assignments, a tutorial set of assignments to do. I've noticed that many of you are sleeping, many of you are wide awake, many of you are participating well. So I will give a set of problems and you will all have to solve those problems on pen and paper and convert it to a PDF where you will write your name, roll numbers on those sheets, either scan it or take photographs and convert it to PDFs, and we will provide you a mechanism to answer them. This is a tutorial. And this is not a test, but it will give me at least some idea of how much you know. And for those who have studied, it will give me an idea to understand and evaluate them for the teacher's assessment as well. So I will give you some of these at 5 o'clock. So if you have time, you please go through the lecture and everything else. I will also upload the slides by this time. Otherwise, you just come and try to solve the problems. But please be ready with pen, paper, and loose sheets of paper or your khatas or whatever. And for the tutorials that I take, I will assume that you all have a copy where you all will solve this in pen and paper and upload it for us to see. With this, I will stop today and you can stop the recording. If anybody has any questions, I will be